230 people died at 30,000 feet. The center wing fuel tank exploded 12 minutes after takeoff.
The ensuing structural failure of that aircraft triggered an exhaustive, highly complex technical investigation. The methodology and the definitive conclusions of that massive effort are detailed entirely within the National Transportation Safety Board Aircraft Accident Report, NTSB/AAR-00/03.
Part 1. Flight and In-Flight Breakup. On July 17, 1996, Transworld Airlines Flight 800, which was operating a Boeing 747-131 with the tail number N93119, was scheduled for a transatlantic flight from John F. Kennedy International Airport to Charles de Gaulle International Airport in Paris. On board, the aircraft carried 212 passengers and 18 crew members. Following a delayed departure, TWA Flight 800 pushed back from Gate 27 at exactly 20:02 Eastern Daylight Time. At 20:18 and 21 seconds, air traffic control cleared the flight for takeoff. The aircraft became airborne from runway 22R at approximately 2019, proceeding on a normal, routine departure and climb sequence over the Atlantic Ocean. Along the way, the pilots received a series of altitude assignments from the Boston Air Route Traffic Control Center. At 20:27 and 47 seconds, the aircraft reached an assigned altitude of 13,000 feet mean sea level. Then, at 20:30 and 18 seconds, the flight crew increased engine thrust in response to a clearance to climb to 15,000 feet. At 20:31 and 12 seconds, while ascending through 13,760 feet, the cockpit voice recorder and the flight data recorder ceased operating simultaneously. This sudden, catastrophic loss of electrical power marked the exact initiation of the in-flight structural breakup.
A critical component of the structural failure analysis focused on the thermal environment inside the Boeing 747 center wing fuel tank. At the time of departure, the tank contained approximately 50 gallons of Jet A fuel. During the aircraft's 2.5-hour delay on the tarmac at JFK, the outside air temperature sat at 82 degrees Fahrenheit. However, directly below the center wing tank, 2 of the aircraft's 3 air conditioning packs operated continuously to cool the cabin. Testing of a representative fuel sample determined the Jet A fuel had a flash point of 114 degrees Fahrenheit. Subsequent flight tests conducted by the safety board using an Evergreen Airlines 747 revealed that the heat generated by those air conditioning packs transferred directly upward. This elevated the temperature of the fuel and vapor inside the center wing tank significantly past its flash point, creating a highly volatile, flammable fuel-air mixture prior to takeoff.
Part 2. Wreckage and Alternative Theories.
Recovering the shattered remains of Flight 800 was a massive, unprecedented 10-month logistical operation. The multi-agency effort, led by the NTSB working alongside the U.S. Navy and the Federal Bureau of Investigation, utilized surface retrieval, side-scan sonar, and trawling operations. Ultimately, they successfully recovered more than 95% of the airplane's structure from the floor of the Atlantic Ocean. Inside a specialized hangar, investigators meticulously assembled 2-dimensional layouts and a massive 3-dimensional reconstruction of the fuselage. The sequencing group correlated the exact wreckage recovery locations with specific structural deformation patterns. This reconstruction demonstrated conclusively that structural failure initiated at the center wing section. The front spar bulged forward in 2 distinct lobes, and the top of span-wise beam 3 rotated forward and down. Forensic examination firmly ruled out a pre-existing structural failure or sudden decompression. Specifically, investigators noted that all 8 latching cams along the bottom of the forward cargo door remained attached to their pins. This definitively confirmed the door was fully closed and locked at the moment of impact.
Public speculation immediately following the crash focused heavily on a high-energy explosive device, but the forensic examinations yielded definitive, opposing results. As detailed verbatim on page 85 of the report, exhaustive analysis of all available medical data on the victims of TWA Flight 800 by an experienced team of forensic pathologists, biomechanists, and criminal investigators failed to find any evidence that any victim was directly exposed to a bomb blast or missile warhead detonation. The FBI did find trace amounts of explosives on a piece of canvas-like material and 2 pieces of floor panel. Yet, metallurgists and fire experts found an absolute, complete absence of high-velocity fragment penetration, severe pitting, cratering, pedaling, or hot gas washing. These are damage characteristics strictly and invariably associated with high-order explosives. Furthermore, controlled testing by the FAA Technical Center determined that explosive residues dissipate completely after just 2 days of immersion in seawater. Because these specific pieces of wreckage were recovered well after 2 days and no corroborating physical damage existed on the metal, the trace elements did not indicate a bomb. The investigation rigorously analyzed the possibility of a surface-to-air or air-to-air missile strike. The physical findings documented on page 246 leave no room for doubt. Based on previous testing performed by the military and FAA, it is inconceivable that a warhead could have detonated in or near the fuselage without leaving evidence of high-velocity fragmentation damage somewhere on the recovered wreckage. Furthermore, the Naval Air Warfare Center Weapons Division evaluated the wreckage extensively. They concluded, as stated on the exact same page of the report, no conclusive evidence of missile impacts exists on any of the recovered wreckage of TWA Flight 800.
The recovered physical evidence consistently and repeatedly eliminated both external threats. Page 259 puts the conclusion plainly. Therefore, the Safety Board concludes that the in-flight breakup of TWA Flight 800 was not initiated by a bomb or a missile strike.
To systematically address the hundreds of civilian witnesses who reported seeing a streak of light followed by a fireball, investigators matched complex trajectory models of the crippled aircraft to observe timelines. Page 265 clarifies this optical phenomenon. Therefore, the Safety Board concludes that the witness observations of a streak of light were not related to a missile and that the streak of light reported by most of these witnesses was burning fuel from the accident airplane in crippled flight during some portion of the post-explosion, pre-impact breakup sequence.
Part 3. Center Wing Tank Explosion. Having eliminated external explosive devices and pre-existing structural faults, the technical investigation focused entirely on the center wing fuel tank. Exhaustive research mapped the internal compartments, fuel-air flammability limits, and potential ignition mechanisms within the Boeing 747-100 wing center section. The synthesis of wreckage sequencing, flight test data, and numerical simulations yielded a definitive root cause. According to page 271, on the basis of the accident airplane's breakup sequence, wreckage damage characteristics, scientific tests and research on fuels, fuel tank explosions, and the conditions in the CWT at the time of the accident, and analysis of witness information, the Safety Board concludes that the TWA Flight 800 in-flight breakup was initiated by a fuel/air explosion in the CWT. The only electrical wiring physically located inside the center wing tank was associated with the Fuel Quantity Indication System, or FQIS. This system measures fuel volume for the cockpit instruments. By design, the voltage supplied to the FQIS wiring is strictly limited, authorized to discharge less than 0.02 millijoules of energy. However, the minimum ignition energy required to ignite Jet A fuel vapor is 0.25 millijoules. For a catastrophic failure to occur, an external voltage bypass was absolutely required.
The investigation formulated the precise ignition sequence that bypassed those safety limits. Step 1. A short circuit occurs outside the center wing tank. Step 2. A higher than intended voltage transfers directly onto the FQIS wiring. Step 3. This energy travels and releases inside the center wing tank, facilitated by an exposed conductor or damaged wire insulation. Step 4. The resulting spark easily exceeds the 0.25 millijoule threshold, instantly igniting the highly flammable fuel-air mixture. Evidence of pre-accident damage, including exposed conductors and silver sulfide deposits, was physically found on recovered FQIS components from the wreckage. Utilizing complex fault tree analysis probability models, engineers from Boeing and the NTSB identified this exact electrical vector. Page 308 of the report identifies the culprit unequivocally. A short circuit producing excess voltage that was transferred to the center wing tank, CWT, fuel quantity indication system wiring is the most likely source of ignition energy for the TWA Flight 800 CWT explosion.
Part 4. Findings and Flammability Reduction.
The structural failure of Flight 800 mandated an immediate global reevaluation of commercial aviation certification standards. The NTSB findings aggressively targeted the systemic engineering logic that allowed unmitigated heat sources to continuously vaporize fuel adjacent to complex electrical systems. The official summation formalized this sequence at the very beginning of the document. On page 1, the determination is absolute. The National Transportation Safety Board determines that the probable cause of the TWA Flight 800 accident was an explosion of the center wing fuel tank, CWT, resulting from ignition of the flammable fuel-air mixture in the tank.
The core engineering vulnerability that allowed this to happen was also defined clearly on page 1. Contributing factors to the accident were the design and certification concept that fuel tank explosions could be prevented solely by precluding all ignition sources, and the design and certification of the Boeing 747 with heat sources located beneath the CWT with no means to reduce the heat transferred into the CWT or to render the fuel vapor in the tank non-flammable.
Moving directly from investigation to industry-wide reform, the NTSB pushed for aggressive regulatory actions. These included the mandatory reevaluation of critical wire separation standards, the immediate proposed substitution of a ground-based cool air supply to prevent tarmac overheating, and the long-term development of in-flight fuel tank nitrogen inerting systems. This push ultimately led to the FAA publishing Notice of Proposed Rulemaking 99-18, specifically designed to minimize fuel tank flammability in both new and existing commercial fleets.
The ultimate structural safety solution relies entirely on neutralizing the volatile environment within the tank. As noted on page 302, although the use of ground sources for conditioned air can provide meaningful short-term benefits, fuel tank inerting appears to be a more promising, near-term method that could even more dramatically reduce fuel tank flammability in the existing fleet.
The comprehensive investigation of TWA Flight 800 laid bare the severe physical vulnerabilities of legacy fuel systems. Did the tragic legacy of TWA Flight 800 permanently eliminate the risk of flammable fuel tank explosions in modern aviation? The answer rests securely in the ongoing enforcement of nitrogen inerting mandates across the global fleet.